Good morning. My name is Neil Polhemus, and the first webinar we'll be doing for 2017 is called Monte Carlo Simulation. I am the Director of Development of the Statgraphics software, and several years ago I decided to put a new item under our Tools menu called Monte Carlo Simulation. The major reason for doing that was to make a little bit more visible the large set of random number generators that we have in Statgraphics. As you'll see in a few minutes, there are over 45 different distributions from which we were generating and can generate random numbers. Now, I was noticing that a lot of people were using Statgraphics to generate those random numbers and then copying them into other applications like Excel and their own simulation models in order to perform Monte Carlo studies. And I thought I could make the whole process a little bit easier by coding some simulation features directly into Statgraphics. Looking back over the webinars that I've done over the last few years, though, I haven't talked about those facilities, so this is a good chance to show you what Statgraphics can do in terms of Monte Carlo simulation. Now, Monte Carlo simulation, incidentally, is all about analyzing models in which random variation plays an important part. The term Monte Carlo obviously refers to gambling, games of chance, and so forth. And an important aspect of any Monte Carlo simulation is the generation of random variables. Now, when I looked at the internet and did a Google search on Monte Carlo simulation, the first thing I found, of course, was a picture of Monte Carlo. And it's sitting there right on the Mediterranean. Very famous, obviously, place to go to play different games of chance. Looking a little farther, I stumbled upon the Investopedia site where they define Monte Carlo simulations as being used to model the probability of various outcomes in processes that can't be predicted exactly. And that's due to the incorporation and intervention of random variables. Looking a little further, I saw a newsletter that MIT had sent out to their alumni talking about how full of complicated systems the world was, with systems in which the variables, the inputs, interacted in complex ways. And noting that because of the probabilistic nature of these models, it was impossible to come up with a definitive or deterministic prediction. And as it says, Monte Carlo simulations essentially use random inputs to model the probable outcomes of different types of systems, different types of models. Okay, so what we are going to be talking about today is the section in Statgraphics under the Tools menu, which is labeled Monte Carlo Simulation. There are three items there. The first has to do with the construction of general simulation models. And we'll be going there in a few minutes to model a particular phenomenon. There's also a section on generating ARIMA time series models, and those are models that can simulate the behavior of random variables over time. And finally, a section of random number generators. Now, the outline for my talk is as follows. I'm going to start by showing you the different random number generators that Statgraphics has. It's very important to be able to generate random numbers when you're doing a Monte Carlo simulation, because as you'll see, they're the fundamental input to the model that lets us assess the probable outcomes. We'll then talk about an example having to do with estimating the amount of oil available in an oil reservoir. We'll look at a volumetric model for the amount of oil in place in a reservoir and see how we can use Monte Carlo simulation to estimate the likely amount of oil available in a reservoir. And then finally, we'll look at a situation where we use an ARIMA time series model to simulate the consumer price index. I'd originally intended to simulate stock prices. Unfortunately, every time I looked at a stock price time series, it turned out simply to be a random walk. So it wasn't very interesting. I did stumble upon, however, the consumer price index, which has a little bit more structure than typically a stock price time series would have. And I think you'll find that a fairly interesting example. Okay, well, let's start talking about the random number generators that are available in Statgraphics. We have random number generators for 7 discrete distributions. Those are distributions like the binomial distribution, the hypergeometric distribution, the Poisson distribution, where the random variable can only take typically integer values. There are random number generators also for 39 different continuous distributions. Things like the normal, the log normal, the Weibull, the extreme value, the gamma distribution, and so forth, which can be used to generate input to a typical Monte Carlo simulation. The random number generators, as you'll see, also allow the user to define their own distributions. We can define our own discrete distribution by specifying each possible value for the random variable x and its probability. And we can also specify our own continuous distributions by giving different values for x together with cumulative probabilities. All of which makes Statgraphics quite flexible with respect to being able to generate random variables. Okay, now I'd like at this point actually to go into the program and show you an example of how we generate random numbers. So let me move over and call up Statgraphics. There it is. And in order to generate random numbers, I'm going to go to the Tools menu down to Monte Carlo Simulation. Okay. And the procedure, I'm going to sort of start backwards, start at the bottom, that I'm interested in is the random number generation procedure. Now, I should remind you, incidentally, that I invite everyone during the course of the webinar to submit any questions. GoToWebinar, which we're using, has quite a good way for you to send us a question, and I'll try to get to as many of those as I can at the end of the webinar. Okay. Anyway, back to the random number generators. What you see here is a dialog box that can be used to generate various types of random numbers. Now, the way it works is you start by defining the name of the column you want to create. And I'll tell it I'd like to create a column called X1 to start off with. You then go to the pull-down list of distributions, and from a fairly long list of distributions, specify the distribution you want to use. And for X1, I think I'll use a gamma distribution. Now, once you select the distribution, another dialog box will come up asking you for the values of the parameters. And a gamma distribution is defined by its shape parameter, its scale parameter, and its threshold. That's the minimum possible value. And I'll just ask for random numbers with a shape of 10, a scale of 2, and press OK. And you can see it put a little indicator into the dialog box that X1 will be random numbers from a gamma distribution. All right, let's define a second column, and I'm going to call this second column X2. And for x2, I think I'll generate some random numbers from a triangular distribution. Now, a triangular distribution is often used if you don't have a good idea of what the distribution actually is, but you do know what the lowest possible value is, the highest possible value, and the most likely value. The triangular distribution I'm going to define will have a lower limit of 0, a central value, that's the most likely value, of 4, and a high value of 10. Okay, so it'll give me numbers between 0 and 10 with a peak in the distribution at 4. Okay, now let's define a third variable as well. Let's define an x3 variable. To define x3, though, I'm going to pick a user-specified discrete distribution. In the case of a user-specified discrete distribution, I'll type in each possible value of the random variable. Here I'm typing in 1, 2, and 3. Those will be the 3 possible values for x3. And then I'll type in some probabilities, 0.2, 0.3, and 0.5, making sure they add up to 1, which will define a discrete probability mass function for me. And for my fourth variable, that'll be called x4. I'm going to create a user-specified continuous distribution. In the case of the continuous distribution, I just put in selected values of x. And I'm going to type in 1, 2, 3, 4, 5. Now it won't generate just 1s, 2s, 3s, 4s, and 5s. Since it's continuous, it'll generate values between those levels as well. Over here where it says f of x, I'll type in the cumulative probabilities. 0 at 1, which means the probability being less than 1 is 0. And then I'll type in 0.1, 0.3, 0.7, and 1 for the cumulative probabilities. I'll press OK. And now I have defined 4 random variables to generate. Now, in addition to defining those random variables, I'll tell it at the top how many I want, and I'm going to ask for 10,000 of each, and tell it where to save it, which is to save it to datasheet A. Now, once I tell it to generate the data, it'll also ask me what sorts of output I'd like to see, and I'll ask for everything. And now what it's done is it's generated 10,000 samples for x1, x2, x3, and x4 according to the distributions that I asked for, and at the same time gives me a summary over here of various statistics, various percentiles, and you can see over here an interesting box and whisker plot and quantile plot for the data. Now, this is the fundamental input that would be used in a typical Monte Carlo simulation. It's not a simulation yet per se, but it is the input for important variables into a simulation model. Okay? And then again, what I can do if I'm doing the simulation in another program, let's say in Excel or something like that, take the data, copy it into that application and use it. Although I'm not going to do that. Instead, I'm going to generate a simulation myself using the other options under Monte Carlo simulation. Okay, but those are the basic random number generators. And incidentally, I just picked a few of those just to illustrate the different possibilities. Okay, now let's go back to my PowerPoint slides for a moment. and talk about how we can use random numbers like this in a general simulation model. In a general Monte Carlo simulation, we begin with some mathematical function. For example, I might have an equation where an output variable y is a function of p different input variables. I'll give you a concrete example of this in a moment, but in general, you see I've got an output and it's going to be a function of p input variables. Now, each of those x variables is a random variable. At least my knowledge is random. They might actually have some particular values, but I may not know exactly what they are. In other cases, they're real random variables with some distribution. In the general simulation model, what I do is I specify a probability distribution for each one of those input variables, for x1 through xp. Okay, probability distribution similar to what we specified a few moments ago when we generated some random values. Okay. The next step will be to generate n sets of random variables, one value for each of the inputs, the x's, plug them into that function. And if you do that, after you do that, you'll get n values for y from which you can calculate various statistics. So that's the general setup. We start with a mathematical equation involving certain input variables. We specify the probability distributions for those variables. We then generate random numbers for the x's, calculate the y's, and compute the statistics for the y's. Okay. Now, let's make this a little bit more concrete. There's a very interesting article by Murtha back in 1994 that had to do with analyzing a volumetric model for the amount of oil in place in the reservoir. He seems to be one of the first people to talk about how you could use Monte Carlo simulation to analyze models for oil in place. If you look at this article, the amount of oil in place, N, which is the number of stock tank barrels of oil in a particular reservoir, can be expressed as 7758, which is a conversion constant to go from, I believe, acres feet into stock tank barrels. It's 7,758 times the area of the reservoir times the net pay of the reservoir times the porosity times 1 minus the water saturation divided by the formation volume factor. And the goal of his analysis was, for a particular site, how can we estimate the number of stock tank barrels that we'll likely be able to extract from that particular reservoir? Okay, so we start with a model. The response variable is the number of stock tank barrels. The input variables are the area, the net pay, the porosity, the water saturation, and the formation volume factor. Okay. Now, unfortunately, when I come to a new site, I don't know exactly what the area of the reservoir is, what the net pay will be, what the porosity is, and so forth. Okay. Those are unknown. The best I can typically do is look at historical data at similar sites to see what they might be, or to use my engineering knowledge to somehow specify the likely values of the inputs. Okay. Now, if you look at this particular equation, you'll see that it won't be very easy to derive the probability distribution for n theoretically, analytically, particularly if we have some complicated distributions for A and H and porosity and so forth. To derive the probability distribution of n, even if we know the probability distributions of the 5 x variables, is not an easy task. Okay? That's when Monte Carlo simulation comes into play. If we can specify the probability distributions for the inputs, for area and net pay and so forth, and generate a lot of random realizations from the probability distributions for the x's, then we can generate a lot of values, potential values for n, and examine that probability distribution. That's at the essence of the Monte Carlo simulation, where we can't necessarily solve things analytically. We can, by simulation, get at least an approximate idea of what the potential distribution of the output is. Okay, now, one of the big problems, of course, if I want to apply that volumetric model, is to get parameter distributions for all of those unknown x's. Okay, I need to know what the probability distribution of area is, and net pay, and porosity, and the other inputs to the model. Now, how do I do it? Well, the way Murtha did it, and the preferable way to do it, would be to find similar sites. And in fact, Murtha found 83 similar reservoirs. Okay? For each of those 83 reservoirs, which have already been worked, we know what the area turned out to be, we know what the porosity was, we know what the water saturation was, and so forth. So we can take the historical data and fit probability distributions. Now, Statgraphics is very good at that. I've talked about the distribution fitting procedures in Statgraphics. It can go take a set of data, go and automatically select the best distribution from a fairly long list of probability distributions. So that would be the preferable way to do it if we had historical data. If we didn't have historical data, one possible approach would be to take a triangular distribution and assume a triangular distribution for each of the x's. Now, a triangular distribution is defined by a minimum value, a most likely value, and a maximum value. And it might be possible, just using engineering knowledge, to specify some reasonable values for a minimum, a most likely value, and a maximum value. And if you don't have historical data, that is sometimes the best approach to take. Okay. Another possible approach is to assume that the distribution of all the x variables is normal, is Gaussian. Specify the mean and standard deviation of each of those normal distributions, and just generate normal random variables every time we do the simulation. Okay. That is sometimes done. A final possible way to approach things is to specify 2 or more percentiles. Actually specify as many percentiles as there are unknown parameters in a particular distribution, and then find a distribution, often a non-normal distribution, which matches the percentiles. And I'll show you an example of that in a minute. Okay, now, as I mentioned, Murtha took the first approach. He went in and analyzed 83 similar reservoirs that had been worked prior to the site he was interested in. And for area, it turned out that a log normal distribution with a mean of 788 and a standard deviation of 906 gave the best fit for the 83 observed values of area. Net pay was also characterized by a log normal distribution. For that particular random variable, it turned out that the mean was 250 and the standard deviation was 227. For porosity, when measured as a percentage, it appeared to follow a normal distribution, and there you can see the normal distribution that we're going to assume for porosity. Water saturation, again as a percentage, was a little bit skewed. So instead of a normal distribution, the distribution fitting procedures selected a gamma distribution. And you can see that that gamma distribution is skewed a little bit to the right. And finally, for the formation volume factor, it appeared that a beta distribution would be most appropriate. Now, a beta distribution generates random values over a fixed interval. And the interval for the formation volume factor is 1 to 2. And it's characterized by two shape parameters. In this case, a shape parameter of 1.14 and a second shape parameter of 9.04. Now, these are all from Murtha's article. As I said, he took some historical data and he fit distributions to the historical data, which we're going to take in a few minutes and use in our simulation. Now, one other possible approach that I mentioned that I want to talk just a couple moments about is the chance of matching percentiles. For example, suppose I didn't have any historical data. I just had some vague idea about what the water saturation at a particular site was likely to be. And suppose I was 90% certain that water saturation would be between 20% and 40%. I also thought it might be skewed a little bit to the right, so I decided I should use a gamma distribution. For the matching percentile approach, okay, what you do is you basically try to find parameters of the gamma distribution, a shape parameter and a scale parameter, such that the cumulative distribution is what you want it to be. So down at the bottom here, I've written f of 20 should be equal to 0.05. That's the cumulative probability at 20%. I wanted that to be 5%. And I wanted the cumulative distribution at 40 to be 0.95. Okay, that gave me a 90% coverage between 20% and 40%. Now, that turns out that's not something that Statgraphics can easily do. However, in the latest release of Statgraphics, we've added an interface to the R language. And this is a great place to actually develop, write, and save in Statgraphics in R script. In fact, I've developed a Statfolio, which I'm going to put up on our website after the webinar, called matchpercentiles.sgp. And what it lets you do is it lets you type in two values for X and two values for the cumulative probabilities, and we'll find the parameters of different distributions that match those particular CDFs. Now, I want to show that to you real quickly because it is a real good application of the R interface that we've added to Statgraphics. I'm going to go to my file menu and load a Statfolio that I've saved called Match Percentiles. Okay, and what this Statfolio will do is it will actually call R, in fact it already called R, and run a sequence of commands. a sequence of commands that I can enter and modify if I like by going to the Analysis Options dialog box. Now this actually script may be useful to you, so I want to take just a moment and show you what the script does. First off, this R script loads the library NLEQSLV. That's a library in R for basically nonlinear equation solving. Okay. In the script, you can see right in this section here, I have set two values for x, 20 and 40, and two values for f of x, I've actually called that p, 0.05 and 0.95. I've then written a function which the nonlinear equation solver will evaluate, which returns the differences between my target p's, my target cumulatives, and the cumulative probabilities of a gamma distribution, of a log normal distribution, and of a normal distribution. I've then asked R to run the nonlinear equation solver to find values of the gamma distribution, value of the parameters, find values of the log normal parameters, and find values of the normal parameters that give me those two cumulative probabilities. The way you can use this, you can load up my Statfolio, and if you need to change x and f of x, just go to Analysis Options. And if you change numbers like the x's here from 20 and 40 to 25 and 45 and press OK, it just called R, and you might have noticed the parameters change. It's now giving me the parameters of a gamma distribution, a log normal distribution, and a normal distribution that match these percentiles instead. Okay. A very interesting, I think, application of the Statgraphics to R interface to use some of the capabilities of R which have not yet been put into Statgraphics. Okay, I wanted you to see that. I am going to post that Statfolio on our website, so if you do need to match parameters of some distributions, you can go ahead and do it. Okay, well, let's close that out for a moment because I now want to actually build the volumetric Monte Carlo simulation for Murtha's model. Now, to analyze Murtha's model, you do the following. You start with an empty data sheet. You define columns for each of the variables in your model. So I'm going to start now and name the first 6 columns of my data sheet. The first column will be called net pay, area. The second column is called net pay. The third column will be called porosity. The fourth column will be called water saturation. Hope I spell everything correctly. The fifth column will be called FVF for formation volume factor. And the sixth column I'll call capital N. That'll be the number of barrels, stock tank barrels of oil in the reservoir. Okay, so I've defined 6 columns of my data sheet. The first 5 columns are the X's. The 6th column is the Y. I'll now go to the Tools menu to Monte Carlo Simulation, General Simulation Models. In this particular dialog box, I will need to define each of the variables. So I'm going to set it up so it has 6 fields. Area in the first field, net pay in the second field, porosity in the third field, water saturation in the fourth, formation volume factor, and number of barrels. Okay, so I first created the columns in the data sheet. Now in the Monte Carlo Simulation dialog box, I'm going to define the variables. Now, for the first 5 variables, those are the x's, I need to specify probability distributions. Now I'm going to follow Murtha, follow his historical data. So for the area, I'm going to use a log normal distribution. And as soon as you choose a distribution, a dialog box will come up asking what the parameters are. And in this case, the mean will be 788 and the standard deviation will be 906. For net pay, I'm also going to use a log normal distribution. Well, Murtha used the log normal, so I'm going to copy his results. It has a mean of 250, a standard deviation of 227. Porosity, it turns out, is pretty normally distributed, so I'll pick a normal distribution. The mean is 29.8 and the standard deviation 5.36. Okay. Water saturation, it turns out, followed a gamma distribution, a shape parameter of 21.56, and a scale parameter of 0.74. And again, these were the results of fitting different distributions to historical data. Okay. Finally, the formation volume factor follows a beta distribution. The shape parameter is 1.14. That's the first shape parameter. The second is 9.04. The lower limit is 1 and the upper limit is 2. Okay, so now I have my 5 x variables defined. To define the output variable, I'm going to tell it that it's a function. And now I'm going to have to type into this dialog box what the function is. Well, what the function is, I'll do this carefully. It's 7758 multiplied by the area, multiplied by the net pay, multiplied by porosity divided by 100. Now the reason I'm dividing porosity by 100 is that the distribution as I specified it was for percent porosity. So I need to correct it by dividing by 100. I'll now multiply by, open parens, 1 minus water saturation, also divided by 100 because it was also a percentage. And then that whole thing is divided by the formation volume factor. Okay, so now I have my 5 x variables and I have my y variable, which is a function of the x's. To actually run the simulation, I'll press OK. And on the next dialog box, tell it how many random samples I want. And I'm going to tell it in this case that I want 10,000 random samples. So what it's going to do is it's going to generate 10,000 random sets of numbers for the x's and evaluate that function 10,000 times. Okay, if I want, I can fix the seed of the random number generator. If I fix it, I'll get the same result as I got the time before. Otherwise, I'll just let it use a random one. Okay. When I press X, the next thing it'll do is ask me what tables and graphs I want, and it's now run the simulation for me. And what it's done is it's generated 10,000 random values for area, for net pay, for porosity, for water saturation, for formation volume factor, and derived 10,000 values for the oil in place. I am particularly interested, of course, in the oil in place. That's why I've done the simulation. And down here, for example, you can see the percentiles. The 50th percentile for oil in place is 1.37 e to the 8th. So that's 137 million barrels. It could be as low, if you look down to the first percentile, as 8.3. Could also be as high as 2.4 e to the 9th, which, if I've done that properly, is actually 2.4 billion barrels. Okay, now we see some graphs here as well. The most interesting graph is probably the quantile plot. A quantile plot is basically a cumulative distribution. Well, at the moment it's area, so I'm going to have to go to pane options. I don't really want to see area. I want to see barrels. There it is. And because of the nature of it, it's probably a good idea to go to graphics options and rescale that x-axis. In fact, it's probably good if I show it as powers of 10, starting at 1,000,000. And let's hold that scaling constant. There we go. And specify the grid. And there you go. I changed to a log scale along the x-axis because of the nature, of course, of that distribution. And you can see this is the cumulative probability. So the median value here is right about here. And you can see the 80th percentile, the 20th percentile, and so forth. That is the primary output of my Monte Carlo simulation. It is my estimated probability distribution for the number of barrels in that oil reservoir. Not just a best guess, but an entire probability distribution given 10,000 simulated values of all the inputs. Okay. Very typical Monte Carlo simulation. You can do that now all within Statgraphics. Okay. Now, back to PowerPoint for a moment. That was the example I wanted to show you of a general simulation model. And you can see all my PowerPoint slides here. I will save the PowerPoint presentation on the website, our website, for you. I'll give you the link to that at the end of the webinar. And you can see all the steps I went through by going through those PowerPoint slides. Now, the final example I wanted to show you has to do with simulating time series. And as I mentioned at the start of the webinar, I had originally thought I would simulate some stock prices, but found out they weren't very interesting since they were just a random walk. I did find, though, a much more interesting time series, which was collected by the Bureau of Labor Statistics. It is the Consumer Price Index based on all urban consumers for all items sampled monthly between 1982 and 2016. Now, it's an index where the value 100, that's sort of the normalized value, occurred someplace, I believe, in 1983. And the higher the consumer price index, that basically the higher prices are. It's the consumer price index is the total price of some basket of goods, a standardized basket of goods. In this case, including all the things you'd like to buy, including oil and televisions and food and automobiles and so forth. And it's averaged across all urban consumers in the United States. Now, if you want to see what the CPI looked like in the last 35 years, you could probably guess what's happened to prices over the last 35 years. They've gone up fairly consistently, except for a little blip in 2008, where they dropped a little bit. Other than that, it's gone up fairly steadily since 1982, average yearly change of about 4.3. And it's been remarkably linear, at least over the last 35 years. If you go back to 1913, when the series actually starts, it's not quite so linear, but over the last 35 years, quite linear. If you want to see it over, I'm sorry, I went too far, over just the last 5 years, it's actually slowed down a little bit over the last 5 years. It's only been rising at an average yearly rate of about 3.2. And it's not quite the straight line that it looked like on the 35-year plot. When you blow it up, you can see that there are some cyclical effects in the CPI. Now, incidentally, what I'm plotting here is the adjusted consumer price index, seasonally adjusted. So supposedly they've taken out any seasonal effects. I say supposedly because I'll show you something that bothered me about this series just a little bit in just a moment. Okay, now what I'm going to do is I'm going to use this consumer price index as the basis for simulating a time series. And what I'm going to do is I'm going to take the CPI data and I'm going to start by fitting an ARIMA time series model to the data. Now, ARIMA stands for Autoregressive Integrated Moving Average. It's a very, very commonly used model. It was popularized by Box and Jenkins way back, I believe, in the 70s, but it's very, very widely used, a parametric model to model different types of time series. As you'll see, it involves autoregressive terms, moving average terms, and I stands for integrated because what you typically do frequently is fit differences of the data and integrate those differences to come up with your final forecasts. So we're going to take the CPI data, we're going to fit an ARIMA model, and based upon that ARIMA model, generate several possible realizations for what might happen to the CPI over the next 5 years. Okay? What is likely to happen to the consumer price index over the next 5 years? Okay? And then I'm going to take those realizations and plot them on a single graph so you can see what sort of variability there is in a stochastic process. Okay, now, why would I do this? Primarily, I would do this if I needed different realizations as an input to some more complicated financial model. As I said, one of the things that people do with Statgraphics is they generate random variables and also random time series, and then move them into other applications, such as a complicated financial simulation, to see what is the possibilities, what could possibly happen with their financial models. Okay, well, let's go back to Statgraphics again, close off what we were doing, and load up the data file. It's a data file I've been working with for a while here. It's called Consumer Price Index. You can see that there is one row here for every month. It starts in January 1982, actually goes through last December. The first step is going to be to generate an ARIMA model for the data. And to do that, I'm going to go to Forecast, and I like the automatic model selection. This is a place I can go, and not only will it fit an ARIMA model, it'll tell me what is the best ARIMA model for the data. I'm going to put in where it says data, the adjusted consumer price index. For the time indices, I'll put date. And just for fun, I'll ask for forecasts for the next 5 years, which is 12 months. I'm sorry, 60 months, which is 5 years. My mind's getting ahead of my mouth. Okay. Anyway, I want 60 months worth of forecasts. Now, it will try models other than ARIMA models if I want it to, but I don't, so I'll uncheck those. I'll have it fit just ARIMA models up to second order autoregressive, second order moving average, up to second differences, and I'll also tell it to include a constant. In terms of how it selects a model, I'll use the default Akaike information criteria. And I'll just take all the defaults, and it turns out that it likes an ARIMA 112 model with a constant. An ARIMA 112 model with a constant is a first order autoregressive model on the first differences with 2 moving average parameters. The order of an ARIMA model is often referred to as PDQ. So P is 1, D is 1, Q is 2. The estimated parameters, and I'm going to need these in a moment, are here. Here's the AR1 parameter, here's the MA1 parameter, here's the MA2 parameter, here's the constant term, and down here is the standard deviation of the errors, which are often called the white noise. Okay. Now I'm going to need those in my simulation. One suggestion that I've already had from one of the attendees is to automatically be able to transfer those numbers to my simulation. Unfortunately, in this case, I'm going to have to type them in, but I will definitely look at the idea of automatically transferring them. It's not too hard, though. Now what I'm going to do, though, is I'm going to go to Tools, Monte Carlo Simulation, ARIMA time series models. And you see here, it's going to give me a chance to simulate some ARIMA models. But in order to do it, I'm going to need to type in the parameters. Okay, won't take long, though. Looking back at the automatic forecasting procedure, the mean turned out to be 0.355178, so I'll type that there. The white noise sigma turned out to be 0.423772, so I'll type that there. Where it says sample size, it means how long a time series do you want to simulate. Well, I'm going to ask it to simulate 61 time periods. Now, why 61? Well, you'll see in a couple moments. Here, I need to specify the order of the model. Well, P is 1, D is 1, Q is 2. The parameters, the AR parameter is minus 0.595915. The first MA parameter is minus 1.12592. and the second AR parameter is minus 0.407999. Okay, so I've put in the AR term and the two MA terms. Okay, if I now go ahead and press OK, I'll take the tables and graphs. I'll press OK, and there is a simulated observation. Okay, that is a simulated time series. Okay, for the time series plot. Okay, Chris?
Yeah.
Would you turn off your mic for a second? Thanks. Sorry about that. Other things happening in the office today. I wanted to make sure that didn't come through on the webinar. All right. Here what we have is a realization of the time series. This is an ARIMA model, a simulated time series, 61 data points. Okay. Now, what I want to do is I want to save this. So I'll go up here to where it says Save Results and ask it to save this time series in a variable called Z1. And what it's going to do, it's going to put it in data sheet B. So I now have one simulated realization of a time series model. I'm going to generate another one. I'm going to go back to the input dialog box, press OK, then press the Save Results and save it again in Z2. Go to the input dialog box again, press OK. And I'm actually going to generate and save 5 realizations of the time series. Okay. Do it again. And go ahead and do it a 5th time. Okay. And you can see every time the realization was a little bit different. If I now go to the data book, data sheet B, we should have 5 realizations. There they are. 61 observations each of the ARIMA model that describes consumer price indices. Now, one thing you will notice is that each of these time series starts at a different place. The first one starts at 20.7, the next at 19.8, the next at 21.2. The reason for that is when we generate an ARIMA time series, we actually generate twice as much data as is requested, throw away the first half, keep the second half. However, I would like them all to start at the same place. So what I'm going to do, watch this, I'm going to go to plot, scatter plots, multiple XY plot. And I'm going to ask it to plot Z1, but not just Z1. Z1 plus 243 minus the index of Z1, 1. That says take the values of Z1, add 243. That was actually the value of the consumer price index at the end of December, the end of the historical time series, and subtract index Z1, 1, which is the first value of Z1. And I'm going to ask to plot that versus count 1, 61, 1. That says count from 1 to 61 by 1 minus 1. Now you'll see what that does. What that does is that forces the time series to start at 243 and plots it 0 to 60. Okay, well, let's actually make it a line plot instead of a point plot. Okay. That's the first realization. Now let's go back to the data input dialog box and let's copy and paste in that same line 4 more times. And in the additional lines, let's put Z2, Z3, Z4, and Z5. And also here, Z2, Z3, Z4, and Z5. Okay. You'll now see 5 realizations, all 5 realizations of the consumer price index starting where it left off in December at 243. Just a little trick there to force all the time series to start where I want them to go. And now you can see 5 potential realizations of that time series, what's likely to happen over the next 5 years. Okay. Well, that's the second example I wanted to show you. I'd also like to go back to my PowerPoint, though, and tell you a little bit about what we're going to be adding to the Monte Carlo simulation. I realized as I was creating that last example that it might be nice if I didn't have to type things like index Z1, 1. So an upcoming enhancement of the time series simulation will be an additional dialog box where you'll be able to get the starting values directly from a time series. So rather than having to type in 243 minus index, it'll pick up the starting values out of a column that you specify. Seems like whenever I do a webinar, I always come up with at least one idea for a good enhancement to the procedures. Okay. And that basically will not only start them automatically at 243, but it'll label the x-axis nicely. All right, well, that is what I wanted to talk about today. I gave you an idea of what is available in Statgraphics for Monte Carlo simulation. We did some random number generation. We simulated an oil reservoir, the amount of oil in place, and we also simulated possible realizations for the consumer price index. I will be adding to our webinars page, which is www.statgraphics.com/webinars, the stat folios, in particular the stat folio for matching percentiles that I showed you, and also the data files, in particular the consumer price index, so you can play with those yourself. And by the end of the day, we'll have the recorded webinar up on the website. Okay, well, I thank you for that. Now let's see if there were any questions that might be interesting to answer. I had gotten a couple of questions before the webinar started, one of which asked, how would we handle an ARIMA model instead of an ARIMA model? Well, an ARIMA model, I didn't mean to end my PowerPoint. Let me just start that up again. An ARIMA model is a model in which there are no differencing. Let me see if I can skip down to the simulation screen here rather than paging through my entire presentation. How about this? Let's see. Excuse me just a moment. I'll figure out how to get to the screen I want in just a second. Anyway, an ARIMA model without the I is a model in which there is no differencing. Okay, that's what I wanted to show. So I called it an ARIMA model because that's the most general case. If you set D to 0, it's an ARIMA model. And there was also a question about what do I do if there's no constant in my model? Well, you can just set the mean to 0 if you need to, and that basically would be a model without a constant. There was a request to transfer the parameters from the forecasting procedure automatically to this screen. Someone indicating that he often has 10 to 12 coefficients in his model. We'll look into whether we can automatically move those parameters. Let's see what other sorts of questions. There were also a number of questions about the autocorrelations of the data in my simulation. By that, I assume they were referring to plots like this of the autocorrelation function of the simulated data, and wondering whether we could do a box Pierce test or something to see whether or not there was no autocorrelation present. In fact, I'm hoping there is autocorrelation in my data. I am trying to simulate a dynamic process. When I do forecasting and I look at the residual autocorrelations, there I'm hoping that I've removed the autocorrelations. Oh, and incidentally, one thing I had meant to complain about, when I fit my ARIMA model to my adjusted CPI, here is the autocorrelation function. You see what amounts to a significant spike at lag 12. That's a significant correlation between observations 12 months apart. This was supposed to be a seasonally adjusted series. That's what the Bureau of Labor Statistics said it was. I would have expected in a seasonally adjusted series that any correlation 12 months apart would have been removed. For whatever reason, in my residuals here, there is still a significant correlation at lag 12, indicating that perhaps it was not completely seasonally adjusted. In the case of the simulated models, however, you're not looking for zero correlation. In fact, you want the correlation to match the correlation of the original time series. Okay. Let me see some of the other questions that people have given me. One was about how I picked particular distributions when I generated the random numbers. I think I mentioned that a little bit later in the webinar. Typically, we try to pick probability distributions that match our data, or if we don't have data, match our knowledge, our process knowledge. There's also a question about how to plot the individual data points in a box plot, a box and whisker plot. Typically, our box and whisker plots simply have points for the outliers. They don't have points for every data point. So I'm not sure what that question had in mind, how to put individual data points in a box plot. No particular way of doing it in our case. We can plot the unusual points, the outside points, but we don't plot all of the points. Here's a question. When you do the ARIMA output and you get an autocorrelation table, it has significant autocorrelations. That was the same question. I'm hoping when I do a simulation, there are significant autocorrelations in the data. That's what I'm trying to reproduce. You see, when I simulate my ARIMA time series model, I'm trying to generate time series with the same autocorrelation pattern as the original data. So hopefully my simulations here have the same general pattern that I would have observed in the original data. Okay, and another question about how do I get an ARIMA model? And again, as I said, you get an ARIMA model by simply setting D to 0. Okay, that is an ARIMA rather than an ARIMA model. Okay, another question, is there a way to superimpose the theoretical distribution function in the histogram of the random values so we can check if enough random numbers have been drawn? That's an interesting idea. In the random number generator, they're asking whether we can superimpose the theoretical distribution function on the histogram. No, the only way to do that would be after you generated some random numbers. For example, if I went into my random number generator and generated some random numbers, let's say some numbers from a gamma distribution with, I forget what I used, maybe 10 and 2, something like that, right? What I could do is I could take that data, I could make a histogram of it, and then potentially superimpose something on it. You see, I could take that into distribution fitting, right, X1, and I could ask it to fit a gamma distribution to the data. Okay, and here, for example, is a gamma and normal distribution fit to the data. And you can look at the estimated parameters of the gamma distribution over here. They're 9.77 and 1.95, close to 10 and 2. So by fitting a distribution, it's not the theoretical distribution, but you can see whether it comes close to the theoretical distribution. And in fact, I generated, right, I specified 10 and 2, and it came out to be 9.8 and 1.9. That sounds pretty close. And you can also see that it does do a pretty good fit to the data. That's the best I can think of. Oh, I knew this question was going to come. Is there a way to do a sensitivity analysis, finding the X that has the biggest influence on Y, using a tornado chart? In this version, no. You'll just have to wait a little while. There certainly will be. That is one of the things that's also being added as a future enhancement, a sensitivity analysis and also a tornado chart. Third, your Monte Carlo simulation assumes that all of the input variables are independent of one another. Can you specify random variables in which there are dependencies between the variables? Again, that's not in the current version, but someone seems to be anticipating a lot of the enhancements that are going to be put into the program. The question there has to do with, when we run an ARIMA model simulation, we assume that the variables are independent of one another. There is no correlation between the multiple variables when we do, for example, this general simulation back here. Another level of complication, if I can go back to that screen, would be to allow for correlation between my input variables when I define the simulation right here. You see, right now we're generating random values for each of these 6 variables. There are cases in practice where those are correlated with each other, and it might be nice to be able to generate random variables with a particular correlation structure. We don't do that at the moment, but again, that is something that is on the way. So that seems to be, Chris, were there other questions I need to answer here? I think I've answered typically most of the questions. If you do have more questions, please send them to me. Neil, N-E-I-L, at statgraphics.com is a good place to send them. Either that or support, and we'll be happy to answer those questions. Okay, for now, I appreciate all your time. I've gone on for about an hour and 15 minutes. So I'm going to end the webinar now. Again, we'll be posting a recording of the webinar sometime this afternoon, as well as the Statfolio and dataset. Have a good day.